Hello everyone. This unit will be demonstrating the integration of rational fractions, particularly with denominators having quadratic factors. For quadratic factors, if we wanted to evaluate an integral wherein it contains a function of x all over a quadratic function, particularly ax squared plus bx plus c times dx, we can resolve this into partial fractions. This will become equal to the integral of a, which is the constant, times the quantity 2ax plus b all over ax squared plus bx plus c, plus b, which is a constant, divided by ax squared plus bx plus c times dx. Let us evaluate this integral. The integral of v squared plus 4v plus 10 all over v cubed plus 2v squared plus 5v times dv. We still can factor out the denominator. So this will be equal to the integral of v squared plus 4v plus 10 all over, factoring out the denominator, we get v times the quantity v squared plus 2v plus 5 times dv. If we will consider the factored out denominator of the integrand, which is v squared plus 4v plus 10 all over v times the quantity v squared plus 2v plus 5, this will be equal to a over v plus b times the quantity 2v plus 2 all over v squared plus 2v plus 5 plus d all over v squared plus 2v plus 5. We shall multiply the least common denominator, which is v times the quantity v squared plus 2v plus 5, to clear out fractions. And multiplying the LCD, we get v squared plus 4v plus 10 is equal to a times the quantity v squared plus 2v plus 5, because v cancels out. And for the second term, v squared plus 2v plus 5 cancels out. So we will be getting here plus b times v times the quantity 2v plus 2. For the third term, v squared plus 2v plus 5 cancels out. So we simply get plus dv. Now that we had cleared out fractions, we can assume the values of the roots of the factors of the equation identity. If we put v is equal to 0, substituting the values will be simplified into 10 is equal to a times 5. From here, we can solve a, which is equal to 2. If we expand the identity further, we get v squared plus 4v plus 10 equals av squared plus 2av plus 5a plus 2b squared plus 2bv plus dv. To solve for the other constants, particularly b and d, we can equate the coefficients of like powers from the identity equation. Let us say we will equate the coefficients of v squared. Equating the coefficients of v squared means the coefficients of v squared on the left side of the equation must be equal to the coefficients of v squared on the right side of the equation. From here, we get 1 is equal to a plus 2b. We took 1 as the coefficient of v squared, which is the first term on the left side. We took a as a coefficient of v squared, which is the first term on the right side. We took 2b as the coefficient of v squared, being the fourth term on the right side of the equation. We know a to be equivalent to 2. So we now can substitute this in the equation. 1 is equal to 2 plus 2b. Now we could solve for the value of b, which is negative 1/2. From the same equation, if we equate the coefficients of v, we get 4 is equal to 2a plus 2b plus d. 4 is taken from the second term on the left side. 2a is taken from the second term on the right side. 2b is taken from the fifth term on the right side. And d is taken from the last term on the right side as the coefficients of v. Knowing the value of a, which is equal to 2, and b, which we just recently solved, which is equivalent to negative 1/2, we now can substitute these values from the equation that we had derived by equating the coefficients of v. Substituting the value of a equals 2 and the value of b equals negative 1/2, we now can solve for the value of d, which is d equals 1. Recalling our integral with a factored denominator, we now can write this in terms of its partial fractions, wherein we have the integral of a over v plus b times the quantity 2v plus 2 all over v squared plus 2v plus 5 plus d all over v squared plus 2v plus 5 times dv. Since we had solved the values of a, b, and d, we will substitute the value of a, which is 2, and b is negative 1/2, and d is 1. If we will expand the integral further, we take the first term to be 2 times the integral of dv over v minus 1/2 times the integral of the quantity 2v plus 2 times dv all over v squared plus 2v plus 5 plus the integral of dv all over the quantity v plus 1 squared plus 2 squared. Here we could say that v squared plus 2v plus 5 is equal to the quantity v plus 1 quantity squared plus 2 squared. Each of the term of this integral can be solved by a certain formula. The first term can be solved by using the logarithm formula, and the result of 2 times the integral of dv over v is 2 times the ln of v. For the second term, we still can solve this using the logarithm formula, wherein if we take the differential of the denominator, the differential of v squared plus 2v plus 5 is exactly the quantity 2v plus 2 times dv. So applying the logarithm formula, we get here negative 1/2 times the ln of v squared plus 2v plus 5. For the third term, we can integrate this by the use of our inverse trigonometric function formula. The denominator is having v plus 1 as a u and 2 will be the a. So here we can apply the arctangent formula. So integrating, we get 1/2 times the arctangent of v plus 1 all over 2 plus the arbitrary constant c.